Good morning and welcome everyone. Today we are going to talk about Akka streams and how Akka streams helped us in one of the projects, in one of the critical projects that we were working on. Just before we get started, how many here have used Akka streams in their projects? Cool. How many are planning to use Akka streams? Very nice. Hopefully, for the rest of the folks, this talk will be a motivation to go back and look at your problem in a way, whether it will fit something like the Akka streams paradigm or stream processing paradigm for your challenges. To start, my name is Sajeev. I am a senior manager with Credit Karma, and here along with me.
My name is Yubin Liang. I'm a staff engineer working on platform engineering at Credit Karma too.
We're both from Credit Karma, and Credit Karma helps make financial progress possible for all of its members, which is right now more than 75 million at this point. Let's jump into the problem. So this is a rough scheme of what we are going to talk about. We'll start with our challenge, the specific problem that we were targeting, how we ended up using a technology like Akka Stream, and then we will go into detail about, technology choosing is one aspect, but making it work, as many of the engineers here knows, making it work is yet another challenge, right? So how did we make it work or adapt for our problem space? And we'll talk a little bit in detail also about back pressure. It's one of the aspects of reactive streams. And finally, we will, before we wrap up, we will talk a little bit about some of the challenges with, it's not all rainbows and unicorns. So there are some challenges with making Akka streams work in your problem space as well. And we face the same challenges and how we worked around some of those challenges. This summarizes our challenge, right? To re-encrypt a huge volume of data. It's Trump huge. And that data is getting live updates, like 24/7. And we have to do all of this while maintaining data integrity and site performance, right? A pretty tall ask. And another way to put this is a key rotation challenge, right? You can clearly see you got some encrypted data sitting, is constantly being accessed, and these are some sensitive data, so you cannot screw up, and you have to rotate the keys, right? And that's pretty much what this challenge is talking about. How huge is huge in Credit Karma or CK? We're talking about trillions of data points, billions of rows, more than 1,000 shards, and hundreds of tables and columns, and tens of applications. So that's the nature of data. Now, this is only painting one aspect of the data. At the same time, we also have a disparity of data. There are some data which is very small. Some tables have few columns that are like encrypted. Some tables have hundreds of columns that are encrypted. And the other aspect is also there are certain type of data that is pretty hot. It is read at a very constant fashion, like too much reads. And some are heavy writes and sporadic reads. So we see like a spectrum of access patterns in there as well. So I'm hoping I've painted a picture of what we are up against with respect to the challenge. How does those business requirements or those translate into like technical requirements? I mentioned there is a huge amount of data, so there needs to be some sort of distributed processing involved. We can't sit there and wait there and then have all of this done in a serial fashion. There needs to be asynchronous processing. We are talking about re-encryption, which is CPU bound and pretty CPU heavy. So there needs to be some sort of concurrent processing. We talked about the live site not getting affected by whatever we are doing, right? So there needs to be some sort of a back pressure. We will go into more detail about back pressure and how it's one of the beautiful things that we discovered on our journey. And finally, no matter what we do, we cannot screw up the live site. So there needs to be data integrity in place. So there needs to be fallback options. Things could go wrong, and so we have to have a fallback mechanism in place. So these were how we translated those business requirements that we started off and then looked at the problem from like the geek perspective. How did we end up with Akka Stream? If you were here yesterday during the keynote, one of the slide clearly mentioned it. Update in place is a cardinal sin when it comes to any kind of like designers. You don't want to do update in place, and that's one of the choice that we made early on, that we are going to keep our source data clean. Whatever re-encryption we are going to do, we're not going to overwrite our source data. So it will be parked in a separate place. Now, there is a cost associated with it, and the cost is the double storage or an extra storage, right? So whatever source you have to have that much storage. That's the only way you can do that extra or keeping the source data clean, because you are writing everything to a separate space. That is one of the decisions that we took early on. Now, based on that, we looked at what are the possible mechanisms for doing this. One was to do a dual write. The second was, can we do something like a message bus? And the third one was, can we reframe this problem and look at like stream processing? So we will go into a little bit more detail into some of these. What is the dual write? Here you have the incoming, the live site that is up and running. It is updating everything to the source. At the same time, we will be modifying the source side, which is, it won't show from here. The source applications will be modified to write to the destination as well using the new key, right? That is one way you can do it. And this will solve if we are starting a table from 0 rows, like a green field, right? But that is not the problem. We have billions of rows sitting in our databases, right? So how do we take care of all the legacy data? And that will be by having an offline migration process that will migrate all that data from the source to the target, right? This is like the simplest approach that we could think of, like. And then we looked at something like a message bus. Can we get it a little bit more interesting, right? So we again go and modify the source applications in such a way that it is now writing to the source table or the original tables, as well as publishing some messages to the message bus, and which will then get picked up by a subscriber and then writes to the target. There are some definite advantages to this, but there are also some challenges with this. Now, one of the challenges is still the problem with what do we do with all the legacy data. You still need to have some sort of a mechanism, some sort of a producer that is sitting and reading all that data and then either publishing it to our message bus or sending it directly, or processing or reprocessing it and directly putting it in the target table. So that was a second approach that we took. And the third one was we reframed this problem slightly differently. We thought we will leave the source applications and their write path the way it is, and then completely take a look from the database standpoint and treat it like a streaming of data from the source to the target. And this is where we were trying out with Akka, right, or the Akka streams. Akka and Akka streams are quite different, but we were looking at Akka streams. Now, in this day and age, in 21st century, wars are fought in Twitter, right? And our best example is our own President Trump fighting wars using his Twitter. And another way to start a flame war is by putting a bunch of geeks in a room and show a comparison metrics like this pitching against technologies. And let me make a disclaimer. The metrics that you're seeing here is how we viewed the problem from critical mass, business requirement and technical requirements. It has nothing to do with whether one technology is better than the other, etc. It's quite dangerous to put a slide like this, but let me run through this real quick. The dual write, it is pretty clear. You are not having a lot of distributed processing. There isn't anything on back pressure. There isn't much of asynchronous processing. You have to change your applications, and we're talking about a lot of applications needs to change. And you still have to do your legacy data migration. Right? With the Kafka, a couple of things definitely change. Right? You bring in asynchronous processing. You definitely bring in distributed processing. You can throw in a cluster there of the Kafka producers, brokers, and consumers. With Akka Stream, things change. Right? We get back pressure, we get asynchronous processing. The applications don't have to change. They are still working the way it is. They are agnostic to everything that is happening. And then finally, there is a legacy data migration that's also taken care of, because you are looking at it purely from a data standpoint, right? From the source to the target. One thing I glossed over, I didn't mention is, once we have built up the target, it is just a matter of you do a table switch and then flip a configuration on the application, and then you are gold, right? Your applications are now using the new key. So that is how, and you can discard the old data that was sitting in the previous source. That's our approach. Anyways, so except for that one red on the bottom there for the distributed processing, the Akka Stream was a clear winner for us, right? So what is Akka Stream? Let me look at it in this way. This is one of the pioneering implementation on the reactive stream processing. You are looking at data processing as a stream, right? So you have data that is coming from one side, and then it is being shuttled to the other side, and while it's being transformed through a pipe, it is getting processed. And in Akka Stream's world, there are three distinct processing stages. One is the source, one is the sink and flow, and the last one is the sink. Source is where you are reading the data from. Right? So you may be reading it from a file system, from a database, from a socket, from a message bus. It can be anywhere. Right? So there will be a source. Now, let me talk about sink first. The sink is where you are finally writing the data. Again, that can go into the same kind of endpoint. It can be a database, file system. It can be a socket, a message bus, anywhere. Now, in between, you have all of this processing of data. Right? So the processing is described in the form of flow. And in flow, you can have multiple flows, you can have parallel flows. It's like a graph at that point. It's a graph of processing. And you can connect many flows. You can see the data is clearly flowing from left to right. Now what makes, I mean, this is nothing new, right? You have data from one end going to the other end. There isn't anything sexy about it. What is sexy about it is the back pressure. And what is back pressure? Back pressure is these data are not just traveling from left to right. They're being pulled from right to left by demand. So what it means is the sink is demanding data from the flow, and flow says, oh, I don't have data. It goes upstream. So that is how the back pressure works. So at no point the sink will get overwhelmed by a fast source. Right? So if you have a very fast upstream, it is not going to overwhelm the downstream, because even if the upstream has a lot of data. You have to hold the data in bounded buffers. And you are holding it there, and you are not pumping it down until the downstream asks for data. So it demands the data upstream. So with that set in context, and that's what makes the Akka stream so valuable for us, and especially given the business requirement that we cannot impact the site performance. How did we go around and tame the stream, or how did we design this whole challenge around the stream processing? And for that, Yubin is going to.
Thank you, Sajeev. So Sajeev just presented the challenge and problem we face at Credit Karma, and also the thought process about how to tackle the problem. So from a very high level, in our view, it's actually really a large-scale data migration problem. So let's take another look at the problem we have. So at the end of the day, our goal is simple, right? We try to do some heavy lifting by moving massive amount of data, right? Really massive amount of data from some source to some destination. And along the way, we try to perform data transformation. And in our case, that transformation is data re-encryption. So let's step back and just do a little bit of imagination, right? Let's imagine there's a magic pipeline we can use just to hook up the source to the destination. And magically, the data just automatically flows through that pipeline from upstream to downstream. And the pipeline can magically perform the re-encryption for us as data passing through. If that happens, then our job is done, and we can all go home, right? If only it's that simple. So that's the metaphor, basically, our design is based on. So let's go a little bit deeper into how we map our vision into the problem. So we decided to use our slave database as the source where we read the data from. And slave database is really a replica of our production master database with a real-time replication. And the decision to use the slave database to read the data is simple. It's try to offload traffic from the master. And we decided to create a shadow table in the master database. Essentially, that's where the data is going into. And the shadow table is basically have identical schema as the original table. And the reason we decided to use the shadow table is twofold. One is to minimize schema change. And second, as Sajeev mentioned, we want to have a 100% fallback mechanism. So in case something goes wrong, any data is corrupted in the shadow table for whatever reason, we can always fall back. So we have a safe net. And for the magic pipeline I was talking about, we try to imagine, and we're going to implement that using the Akka stream, the source flow and sync pipeline. And then we have to model the data as a stream, right? So what is a stream? At the end, a stream is basically an open-ended data sequence. So we have to order the data in some way. And luckily, for all the tables we are migrating, they already have an auto timestamp column, which essentially captures the last modified date. So every time a row is updated or inserted, the current system time of the database is captured and set into that field. And then with this field, we can basically order the data as a sequence, and also as live data come in, they will have a more updated recent timestamp. In this way, they just naturally go to the end of the stream, and this data sequence never ends. It's open-ended, just naturally fit into the stream, right? As long as we serve live traffic, data will be updated or inserted, they will naturally go to the end of the stream. So basically, that really drives our design about how to solve the problem. So we fetch data in batches from the slave. So each time we fetch a fixed size of data, depends on our memory constraint. And then we encrypt the data, and then finally, after encryption, we insert them into the shadow table. And we will use the timestamp, as I mentioned earlier, as a watermark or as a cursor, basically to keep track of migration progress. So we do the migration progressively, right? And then the re-encryption will be done concurrently, because this re-encryption is CPU intensive. We need to decrypt using the old key and encrypt again using the new key. And finally, once it's time to write to the database, we want to do it in a very controlled fashion. We want to control our migration pace without adding, or try to minimize the load try to minimize the increased load on the master database, because that's the database serving live traffic, and we try our best not to disrupt any, try to not cause any disruption to live traffic. So this is a bit, the detailed view of how we build the pipeline. So in between the source and the destination is our Akka stream pipeline. And we implement the source using an iterator. And the flow will be running in multiple threads concurrently to do the re-encryption. And that's to take advantage of multiple CPU. And at the end, all those data will be aggregated and sent to the sink to be serialized into the database sequentially. So we will break the data further into smaller chunks and before we write to the database. So I'm going to show you a little bit of animation just to show how the overall flow works. So we start by fetching a batch of records from the slave database. And we use the order by based on the last modified time. And we always fetch a fixed size, depends on our memory constraint. And once they are fetched into memory, then we build the pipeline. That's where we attach the source as an iterator on top of the batch of records, and then hook them into the flow, and in turn send them to the sink. That's where the whole graph is built. And then the flow will fetch a bunch of records based on a predefined group size and concurrency level. So it will fetch from the batch of records from the source and break them into groups of equal size. And then each group will be running their own threads concurrently in parallel. And after all those groups of records are re-encrypted, and they are aggregated and sent to the sink one by one. The order in this case is not important. The group order can be in any order. And then the sink will just break them apart into further smaller chunks and generate the SQL query and write them one by one into the master database. And now at the end of the batch processing, our cursor is advanced. And then we will read the next batch from the slave again. And this whole process just repeats itself. So that's, in a nutshell, how the overall flow works. So here's some code snippet how we fetch data. It's very simple. We just do an order by auto timestamp and always fetch based on a fixed batch size, which is configurable, depends on our memory constraint. And the cursor is updated at the end of the batch processing. So we always use the cursor to keep track of, as a watermark, to keep track where the last step is, and then continue as we move along, migrating the original table, batch by batch. So the source is created only after the batch is fetched from the database. And we made a deliberate decision not to tie the source directly to a single database. And I'm going to talk about that reasoning later on. So the source is very fast. Essentially, it's just an iterator in memory, right? So you fetch the whole batch in memory, then just iterate through them. So the iterator is really driven by the flow. And this part is single-threaded. And as you can see, there's no processing at all. It's just iterating in memory, which is very fast. So to implement the iterator interface is also simple, right? So the data sequence is already fetched in memory. So we simply implement the next and has next. Has next indicates it's already reached the end of the batch. And the next is called every time the flow tries to fetch the next record, it just calls flow. The flow will just call next. The flow is really the heavy-duty part, right, which does all the re-encryption of all those data. And it's running in parallel. And we configure the group size and the concurrency level also based on our resource constraint. And one thing to note is the group size is much smaller than the batch. So the batch is basically we just do a one-shot, fetch them into memory, then depends on our concurrency level and group size, we break them into smaller groups. And then each time only a subset of the group is executed by the flow. And this part, since it's more heavy duty, it's more CPU intensive, it's relatively slower, but however, it's done concurrently. So this is some code snippet to show how we establish the flow. Right? So we just do a group by based on the group size. And then since the order of groups sent to the sink is not important, we just use a map as synchronized, map async unordered, so that we can send, as soon as a group is finished, we can send to the way of the sink as soon as possible to maximize parallelism. And all the re-encryption is done concurrently using threads in the Akka thread pool. And finally is the sink. So this is where data is being written to the master database. And it's single-threaded, and we had to be very cautious at this stage because this will potentially cause increased load on the production database and may cause disruption to live traffic. So we have to do it in a very controlled fashion, and we have to monitor very carefully. And here we break the group further into smaller chunks, and we generate the final insert query and then insert them into the database. So some snippet to show the sink is just does a for each. So basically, as soon as a group of records is finished processing by the flow, it sends to the sink, and it just iterates through each group it receives as a sequence of records, and break them apart into smaller chunks and generate the SQL query. And we use the insert on duplicate key update to allow retries, because there could be errors, right? While writing to the database, there could be data errors when the re-encryption had issues. You use the wrong key for whatever reason. So we want to be able to retry. So we use the insert on duplicate key so that for new records, it will be an insert operation. For existing record, if we try to write twice, it will simply be an update. It won't generate errors. And I couldn't stress more, this may cause a performance impact on database, so we have to be super careful here at this stage. So this is basically a typical setup to use back pressure, because we have a fast source, a relatively slower flow running concurrently, and then eventually everything goes to the sink, which is the slowest part. Single-threaded, IO bound, everything is done sequentially, and we will really want to control our migration pace to minimize the load on production database. So luckily, Akka Stream has back pressure built in for us. So why do we need back pressure? The reason is very simple and obvious, right? We don't want to drink from a fire hose. We never want to be overwhelmed by things that we cannot keep up with. So the way back pressure works in Akka Stream is basically the flow only pulls from the source after you finish processing a group of records. So it's not being pushed by the source. It's actually pulled. The flow will pull from the source after it's finished, as soon as they finish processing a group. And then the flow won't start sending data to the sink until the sink already finished processing all the groups that's already received from previous flow processing. And as the flow pull from the source, it just calls the iterator next. Basically, it pulls them one by one, and then until it reaches the size of the group. Then it will start processing using a thread, and then after it's done, it will send to the sink, and then another group will be started, all in parallel. And to use the back pressure, we really have to know when the end of the batch is finished. The last record in the source is finished processing. And there's no way to know because everything is done asynchronously and in a parallel fashion, right? The source and flow sync all running in their own threads. So after we establish the pipeline by connecting the source to the flow and in turn to the sink, after we start running the whole pipeline, running the group, it returns back a filter. And that filter won't be completed until the last element in the source is finished by the sink, which means the sink writing the last element into the database. At that time, the filter will be completed. It could be either success or failure. If it's success, then we know the batch processing is complete, and we are able to advance the cursor. If it's a failure, then basically we have to start all over again. And the throughput, as you can see, is really controlled by how fast we drain the source. It's not by how fast we read the data. It's by how fast we actually write the data to the master database. And this is some trace messages we printed out during a test run in our migration program. And we add the trace message at the beginning and at the end of each processing stage. So as you can see, the flow are started. Here we use a concurrency level of 3, just to show the point. So here you can see the flows are all started in parallel using different Akka threads. You can see the thread IDs are all different. And after flows are started, and as soon as one flow is completed, it will start fetching from the source. And then after those groups are sent to the sink is starting to process them one by one. So as you can see, as the flow finishes, the sink starts. So we add a trace message at the beginning and the end. And so you can see the sink is really started one at a time. It's really sequential. And it's all done in a single thread. So it's only one. After the previous group is finished, then the second group will start by the sink. And only after the sink finished syncing all the groups it has from the previous flow, then the next batch of flow starts concurrently. So essentially, from end to end, that's how backpressure works. So they are all running like in a staggered fashion. And it's totally controlled by how fast we sync the data. So here I'm showing some animation just to show end-to-end how backpressure works. So after we fetch from the slave database, based on the group size, right, they can be partitioned into groups of equal size. We only fetch the number of groups based on our concurrency level, based on how many threads we assign to run those groups. And at the end, after the flow finished processing each group, they are sent to the sink. But in the meantime, they are fetching from the source. So it's all running in parallel. So they are sent, as soon as they finish processing a group, it sends to the sink, and also it pulls from the source, all happening at the same time. And then the sink will basically sync them sequentially. And then after it finishes syncing all the groups, then it pulls from the flow again, and then process them one by one. So just to show how the backpressure works in real production traffic, so we captured some data from our production. So here, during some period of time, during our data migration of some particular table, we observed increased traffic on our left side. So during this period of time, our site traffic increased. Our throughput also increased. And that translated into increased database operations. The number of DB operations increased accordingly. And then we observe increased latency on database access. So when we sync the data, the latency increased. And our migration throughput start to degrade. So it's all happening at the same time. However, as you can see, even our throughput is degrading. It's actually degrading gracefully. It's not like any sudden drop, because our resource resource consumption remains stable through the whole time. Our memory usage, our CPU usage, our load average, it's all stay flat. The load average even dropped a little bit.
Yeah, just to interject, if this is not what back pressure is, I don't know what is, right? So you can see the nice degradation on the graceful degradation on the throughput, even though our databases were getting hammered during the same time. So we pulled back as the site traffic went up, right? So you could clearly see from these graphs how back pressure was kicking in, the CPUs and even the load average was dropping because we were processing less, because the demand has dropped because the site was getting like hammered at that time.
Yeah, this really serves us well because our top priority is not disrupt the site traffic, right? Our data migration can take time in a controlled fashion with our own controlled pace. However, absolutely, we don't want to cause any disruption to site traffic. So we simply degrade gracefully. So far, everything works in our way, and Akka Stream basically works magically, basically to build this pipeline that we imagined earlier. But however, there are some limitations that we run into. I'm going to cover next. So in a simple world, we can have a single, if we only have a simple, very simple, small database, we can have a very simple setup, right? We can have a single JVM hosting the Akka Stream, and then we connect the source directly to the destination. However, our case is a little more complicated. So as we mentioned earlier, we have many sharded DBs. We have over 1,000 DB shards. And apparently, we can't do all those tasks with a single JVM. We had to have multiple JVMs. We need a JVM cluster hosting those Akka streams. And the volume of data is also huge. So the question we need to ask is, how can we evenly distribute the load, right? So that we don't have a single shard that receiving all the migration traffic. We won't run into a hard shard issue. And also, we won't have a single JVM does all the heavy duty work. So we won't run into an issue where a JVM is overloaded. So how can we evenly distribute the load among all those JVMs, and also evenly distribute the traffic among all those DB shards? So that leads us to ask the following question. Can we have a distributed Akka stream? Can we have the processing stage of source, flow, and sink all running across the JVM boundary remotely in a distributed fashion? For example, can we have some JVMs hosting the source and then pumping the data to the flow hosting by some other JVMs, and then they will do all the heavy-duty CPU-intensive re-encryption. At the end, they will just aggregate the data and send to the final sink, which, again, one or more JVMs running the sink processing stage and write them to the disk. Can we have some kind of topology like this? And based on our research, this is not natively supported by Akka Stream out of the box. And one reason is it may run into deadlocks, where you apply back pressure both ways, and in case some messages is lost over the wire, because all those are running remotely. So there could be corner cases that you run into. So what's our solution to overcome this limitation? So our solution is basically divide the work based on shards. Since we have so many DB shards, we can simply divide the work based on around the shard. So our way is basically abstract the workload by wrapping a task around a particular table in a particular shard. And in the task, we capture the metadata information such as the table name, the table that we are trying to migrate, the shard information, the watermark, the timestamp cursor, and all those information is basically captured as a single unit of working task. And then we build a work queue to group those tasks. And then those queues can be distributed among JVMs running Akka streams, and the load will be evenly distributed. So our topology works like this. So we have a big DB shards, and in the middle we have a relatively much smaller JVM cluster hosting the Akka stream internally, and the Akka stream is all running local within each JVM. And then each JVM will simply fetch a particular task from a work queue, which corresponds to a particular shard. So this way, we totally decouple the database from the JVM. Remember earlier we mentioned we made the deliberate decision not to tie the source directly to a particular DB, and that's the reason. So it's totally separated and loosely coupled. And this way we can scale the shard and the JVM cluster independently. We can scale them down, scale them up, scale them down, and they don't have dependency on each other. All the JVM cares what's the next task for me to run. And that task can translate into any DB shard, any table. And we keep track of all the progress, all the cursor in each table, in each shard. This is how the work queue looks like. So basically, we generate all those tasks in the work queue, and they will be ready to run, ready to be picked up by any JVM in the JVM cluster hosting the Akka stream. And once the JVM is ready to run the next task, it will simply dequeue from this work queue and start running them. And that task basically translates into a particular table in a particular shard based on the current cursor. And after the JVM finishes processing a batch from this task, it will advance the cursor and set the cursor into the task, and then put them back into the queue. And then we'll pick up the next task to run. So some tasks may be more heavy duty than others for the reason that at the beginning of the migration, we have more records to migrate. However, as the migration progresses to the end, basically only the live update records will be migrated because all data is already migrated. So towards the end, the workload will be much smaller comparing to the beginning of the migration for a particular table. So basically, we keep track of all those information, and also we keep track what's the processing time, because we have a big disparity between tables. Some table may have more rows, but fewer columns, and some table may have more columns, but fewer rows. So we need to keep track of all those processing time for each batch. So as the JVM completes processing each task, it knows how heavy that task is. And we can build some heuristic dequeue strategy to process lightweight tasks more often than heavyweight tasks, to distribute the load even more. So we wouldn't run into like hard shard or hard JVM issue. So this is how we dequeue. Basically, we use a database table to implement this task queue. And the way to dequeue is simply fetching the next task in the queue where the state is in ready state. And then as soon as the JVM fetch that task, it sets the state to running. So all this is done in a single transaction. So we do a select for update first, then we update the state to running. And this way we prevent any concurrent access to a particular task to enforce that no single task is run by two JVMs. Otherwise it will be a disaster, right? You have two JVMs running the same data all at the same time. You may have data corruption. The benefit is obvious, right? So we still keep the promise of running the Akka stream local in each JVM without crossing the boundary. We all know the limitation. The JVMs are totally stateless. They don't care which task they run, right? After it finishes processing a task, it's just sent back to the queue for the next JVM to pick up. And there's no dependency between JVMs. They're all running independently. There's no communication between the JVMs. And also the shards and JVMs are all loosely coupled. And we can scale them up and down totally independently. And also any failed task, like for example, if there's a DB access error by a particular JVM, it will simply put it back to the queue to be retried by the next JVM, right? Because some JVM may crash, may lose their DB connection. So at the end of the day, it doesn't matter. All those failed tasks will simply go back to the queue and will be retried by the next available JVM when it comes. And also, if we have a crashed JVM, some JVMs down, it won't block the migration of the shards because other JVM in the cluster can just take up the work. And also, a single failed shard won't block any JVM because the JVM will just skip this shard and fetch other shards because we don't have a tight couple between the JVM and the shard, right? So any side is down, it doesn't matter because other available JVMs or available DB shards will be served the next task. Error recovery. So after we finish completing a task, which essentially finish batch processing for a table, then they will be sent back to the queue with the cursor updated. Otherwise, we send it back to the queue, cursor not updated, which means the cursor will remain as it was before because our batch processing failed, right? Then it will be retried. Next time the task is fetched by another JVM, we'll simply retry. However, we want to fail fast. If we notice there's a fatal error, which is not retriable, we'll simply mark it down so it won't be picked up by the next JVM, right? It's not worth the time. The next JVM, once it's available, it will just pick up whoever is in a healthy state. It will simply skip the one with the fatal error. And also, in case of data corruption or any disaster happen, we can simply reset back the cursor. The worst case is we reset the cursor back to the beginning of the table and just restart all over again. So nothing basically will cause any really a dead end for us. We can always have a safe net to fall back to. So with that, I'm going to invite Sajeev to tie the loop.
All right, thanks, Yuban. So we are about to wrap up. I know we are running a little late. We started late, so hopefully we can wrap it up within our 15 minutes. This is how we started, right? These were the technical requirements with which we started. We wanted to have all of these cool things. And how did we bring all of this to our system? For the distributed processing, as Yuban mentioned, right, one of the whirlpool that we ran into where Akka stream cannot remote out of the JVM, we built a task distributed mechanism on top of it. And I would say that in the previous talk also, in the keynote, it was mentioned like little Chinatowns. So you can think of the Akka stream, everything running in a single JVM as a little Chinatown. And then if you want to now partition, so it is very efficient within that because it's within the JVM, everything is in memory. Everything is message-based, right? Now, if you need to now make it distributed, go upstream, look at your source of the stream, and see whether there is any way you can partition it based on that. And that's what precisely we did. We went upstream, we looked at our shard mechanism, and used that as our vehicle for making it more distributed. For the asynchronous processing, we relied on Akka streams. For concurrent processing, we relied on Akka stream. For back pressure, Akka stream. I mean, there is a pattern emerging here. No, for the fallback, we used a shadow table approach, right? So, this is one of the things that I mentioned at the beginning. We have a source and a target, and we are not polluting the source. So this is the shadow table. So that's how we ended up solving or meeting our technical requirements. I tell you, Akka streams really came to our rescue with most of the things that are mentioned here. And finally, some of the key takeaways. Some of the stuff, these are definitely software architecture principles, good practices that we cannot reinforce or we cannot reinforce enough. Make your whatever you can configure, configurable, or most of the stuff. And in our case, it was our batch size, the read batch size, the write batch size, the concurrency, the number of groups. We made a lot of things configurable there. And it really, really helped us because we were tuning it with, I mean, as I mentioned at the beginning, there were the disparity of data, right? The large tables, like large as in like fatty tables, and then lean tables, but a lot of data tables. So we have to be flexible to pick either one, and sometimes we use some of these configurations to adjust how we were processing the data. Yuban?
Yeah, another important perspective is to be able to basically make your service adaptive, right? The traffic to our left side can increase at any time. The DB load can increase at any time, and we have a big disparity among our tables that we are migrating. So any table we are migrating may have different load, just varies, right? So we should really be able to adapt to the changes on the fly and make adjustments.
The third one in there, being observable, right? Flying blind is the last thing you want when you have a big complex system in place. So we had extensive logging, capturing stats wherever we can, and those were really our guiding forces in deciding like some of the performance tuning, batch tuning, the batch tuning, the configurations that I mentioned earlier. So really highly recommend making your applications observable.
And the last, but definitely not the least, is retryable. I couldn't stress it more. Any errors, we should be able to retry. We should have the expectation to handle failures. Right? Failures are definitely going to happen. Right? Anything can go wrong, will go wrong. We need to have that mindset. So in case of failures, we just need to be ready to handle them.
And with that, we are wrapping up. Kritikama is hiring, so just so you know. If you have any questions, let us know. I think. Oh.
How does Akka compare with, say, Apache NiFi?
What's the question?
We can't hear that question. Can you repeat that question, please?
How does Akka compare with Apache NiFi?
Apache.
Kafka?
Apache NiFi.
Oh, NiFi? How does Akka Stream compare with? Oh no, we didn't go into the evaluation of using that tool. So
because it is distributed and it has back pressure and all that.
Yeah.
I don't know if I haven't worked with Akka, so I don't know how it compares. That's why I was asking.
We did not go into the evaluation of that.
Okay.
And this worked out beautifully for us.
Okay. And did you do any benchmarking comparing Akka streams with Kafka streams?
Kafka streams, yeah, I don't know, because Kafka itself doesn't have back pressure, right? So maybe it's another stream on top of Kafka, but however,
Yes.
you need its own cluster, right? And it's not in memory, right? So basically, in our case, our implementation is very, very lightweight. Everything is within the JVM. Everything is fetched in memory, and we just have the back pressure flow all the way. So it's very lightweight. We don't need a separate cluster setup for Kafka or any other technology.
Yeah, those were some of the choices.
We have a very small set of JVMs.
Yeah.
Right? Just a couple of boxes to migrate trillions of rows.
Okay, thank you. And will this slide be available?
Should be.
Okay, thank you.
MySQL.
Yeah. It's MySQL. So,
Well, our MySQL is all sharded. I don't know what you mean distributed database.
no, actually, I mean,
Cassandra. Yeah, it's all legacy data.
yeah.
So,
So,
That's why you have.
yeah.
exactly.
Yeah, serving production traffic. Yeah,
We're talking about-
we can't disrupt that.
One more thing is, have you ever thought about using event sourcing? That instead of reading the source directly, and then you just read it and create the events, then let the small microservices.
Yeah, essentially,
straight
you know,
to their read side.
yeah, in our case, we treat the events as really the data itself, right? We just read through the data, and basically our database is the true source. There's no reason to add another layer to do the translation. Yeah.
Yeah. Regarding the distributed databases, right? We are working with like petabytes of data sitting in MySQL, and this is like legacy, like 10 years worth of data. Yeah.
Yeah.
I mean, like, I see this kind of application that they use Spark and distribute
Yeah, yeah.
and like, migrating data.
Yeah.
Yeah, we just want to do something very minimal, just serve our own need. And we feel this solution is very lightweight. It doesn't require any additional setup. It's very efficient.
Yeah, by the way, all this back pressure, Akka stream, everything, the code base looks very minimal. And that was one of the beauty of this. Like you just write source, flow and sync, and then you connect them to a graph, and you are kind of done. Most of our code base is the task distributor that we built on top of it. The Akka stream itself was very lightweight.
And it really simplifies the implementation.
Yeah. Yes. We'll be around if you have, because there is going to be another talk in another 10 minutes. Please find us. Thank you all for coming.
Thank you.